Welcome everyone. In this video we will use Gauss's law, which I derived in the previous video, to calculate the electric field due to an infinite line of charge, infinite wire, and it is charged. So we have a line like this. As I said, it is a wire, and it has an incredibly small thickness like this, and it is charged. As I said, it is positively charged, let's say. Now this has a uniform charge density, which I will represent with lambda, and the unit of lambda is as follows. So when I put brackets around lambda, it means its unit, and it is equal to coulombs per meter. So as I said, we have an infinite line of charge, and you might be asking, how can we have an infinite line of charge? Well, if you don't want to think that abstractly, you can say that we have a very long wire, charged wire, and we are at a point really close to it. So if you are very, very close to a long wire, it will appear as if it is infinite, right? Imagine you are an ant and you are very close to a long wire. It may appear as if it just goes on forever. So you can think of it like that as well. Now, we are interested in finding the electric field at this point, let's say. So we are asking, what is the electric field here at point R? Well, the first thing to notice is the electric field will be to the right. And how is that? Why is that? Well, because it can't have an up or down or away from the screen or to the screen component, because since this is an infinite or a long wire, every component, let's say if this point creates a field in this direction, then this point will create a field in this direction, and these the vertical components will always cancel each other. So we will only have a component that is pointing to the right, that will be away from the wire, right? Of course, if we were at this point, it would be to the left, right, from symmetry, of course. I hope this point is clear. And since we got this out of the way, now we can use Gauss's law. And to use Gauss's law, I will draw ourselves a cylinder like this. And actually, I want to make it in a different color with green. So we have a cylinder like this. It is a closed surface, as you guys can see. Now, let's say that our cylinder has length L, and of course our wire continues all the way like this. Let's say that the cylinder has a length L and its radius is R. Now, if you remember Gauss's law, which I derived in the old video, in the previous video, as I said, Gauss's law tells us that if we compute the dot product over a closed surface, we get the charge that is inside divided by epsilon naught. All right, this is what Gauss's law says, and we proved this for the case of a sphere. Now, to use this for our case, we will think of the electric field lines. For all the points inside our inside our cylinder, excuse me. Maybe we have electric lines like this, like this, like this. But notice that, as I discussed with my symmetry argument, no electric field line will be like this. So since we are taking a dot product, at the end of the day, these upper surfaces, they won't have anything to do with our calculation, because all the time, since we draw their ds vectors like this, all the time the electric field and their surface vectors will be perpendicular to each other, and if we multiply perpendicular vectors, using dot product, then we get 0 because cosine of 90 degrees is 0. So the only contribution will be made by the side surface of our cylinder. So I want to draw the side surface here. We know that if we wrap it out, if we think of the cylinder by its surfaces, we can think of it with 3 surfaces like this. This one and this one. And as I said, these two won't do any contributions because we are taking a dot product. Only this rectangle will give us a contribution to our calculation. And we know that it is with a length of L. And what is the other side's length? Well, think of it like this. The circles that we have here, they completely surround this side of our rectangle. So the circumference of our circle should give us the length of this other side. What is the circumference of a circle with radius r? It is simply 2 pi r. So this length is 2 pi r. Well, this means that this area is 2 pi r times L. Right? That's how you find the area of a rectangle. So now we are ready to go. Now, using Gauss's law, we can take E out, and without a arrow, it simply means the magnitude of the electric field. We took it out because at our distance, all E's have the same value. We have ds is equal to q inside. Well, what is the q that is inside? It is simply the charge density times the length, right? If you refer back to the definition of lambda that we made here, you can understand how this is correct. Then we divide by epsilon naught. Now we have E, and the closed surface integral of ds will simply give us the whole surface area, which we just computed to be 2 pi r L is equal to lambda L epsilon naught. We see that L's cancel, and this is great because you could have chosen any L, right? We just made an arbitrary choice there. It shouldn't depend on L. It was a personal choice that we made, and it is great that it cancels. So this leaves us with that E is equal to lambda divided by 2 pi epsilon naught r. Of course, this is the magnitude of our electric field. If we are interested in its direction as well, if we are interested in the vector form, we would put a vector here and we would need to denote direction. Well, to denote direction, we will say that it is in the radial direction. We put an r hat there, and this is our final answer. As you can see, Gauss's law can be very helpful to find electric fields created by symmetrical distributions of charge. I hope you found this video helpful. If you have any questions or comments, please write them in the comment section. I hope to see you in another video. Until then, take care.